Well, welcome back. This is the second part of Lesson 2 on points, lines, and planes. And in our last lesson, we talked about how to name different points and lines and rays and what an opposite ray was and how we label planes. We're going to be using that information in this lesson to figure out the intersection of different figures that we talked about from our last lesson. So to start off with, a couple new vocabulary words that you need to be familiar with is a postulate or an axiom, and those are just fancy words for statements that we are going to accept as fact. And they are very similar to undefined terms that we talked about, like points, lines, and planes, that we're going to use as building blocks for our logical system in geometry. We are going to use logical reasoning to prove general concepts in this course. So this is going to help us as we move along the path to doing logical proofs in geometry. So our first postulate, postulate 1.1, says that through any 2 points there is exactly one line. Okay, and here's an example. If we have points A and point B, there is only one line, and that's line T right here, that contains both of those points. So any 2 points there's only one line that contains those 2 points. That's our first postulate. When we have more than one geometric figure, if we have 2 or more, and they intersect somewhere, that intersection is the set of points that they have in common. So for example, in postulate 1.2, say we have 2 intersecting lines, and these lines are different, then they intersect in exactly 1 point. In the example we have here, line AE and line DB intersect in point C. And then postulate 1.3 tells us that if we have 2 planes that intersect, okay, here we have 2 planes. Now remember, a plane, this is represented by a rectangle, but it actually goes on forever in all 4 directions, okay? So we have plane RST and plane WST, and they intersect in a line right here, and that is line ST. So whenever you have the intersection of 2 separate planes, 2 distinct planes, they will intersect in a line. It will never be a segment. It will never be a point. It's always going to be an entire line. All right, so if we know 2 points that 2 planes have in common, we can use those previous postulates to find the intersection of the planes. So let's take a look at a problem. Here's problem 3, finding the intersection of 2 planes. And we're going to use this cube that we have over here on the right hand side. And it says each surface of the box at the right represents part of a plane. What is the intersection of plane ADC and plane BFG? Well, plane ADC, I put a little hint here, is shaded in the top. That's the top surface. And plane BFG, over here, that's the one on the right surface. So those 2 planes intersect, and we want to know what is the intersection of those 2 planes. Well, our previous postulate tells us that the intersection of 2 planes is a straight line. It's a single line. So those two planes will intersect in a single line that contains the 2 points that are on those edges, which is line BC. So what do you think? What are the names of 2 planes that intersect in line BF? So this time we have BF down here. Can you name 2 planes that would intersect in line BF? Go ahead and pause the video and see if you can come up with an answer for that one. All right, I don't have a lot of room, so I'm going to write up here. So the 2 planes that intersect in line BF, now BF is this vertical line right here. So you're going to have plane BCG and plane, let's see, it would be ABF. You may have used different letters to label those, and that's totally fine, but it's going to be the plane in the front right here and the plane on the right. Those are the 2 that will intersect to give you line BF. Postulate 1.4 says, through any 3 non-collinear points. Now remember, non-collinear means they're not in a line. So not all three of them can't be in the same line. So if you have three non-collinear points, there is exactly one plane. Okay, so any 3 points, it takes 3 points to determine a plane is another way of saying that. So here's an example. Q, R, and S are non-collinear. So plane P is the only plane that contains those 3 points. Okay, plane P is unique then. There is no other plane that contains those 3. So let's take a look at some problems here. What plane contains points N, P, and Q? Shade the plane. So we have N, P, and Q, and that looks like the bottom surface. So here's a picture for you. You don't have to draw the picture. If you want to just shade it in your notes, you can do that and just say that it's the bottom plane. What plane contains points J, M, and Q? Well, we have J, M, and then Q is over here. So this one is a little bit different. It contains an edge on the top, but then it's going to go down diagonally to Q. So then J will connect to P as well. So here's a picture of what that would look like. It's kind of a slanted plane. Here's one for you to try. I went ahead and gave you a copy of the picture from the last slide. The question is, what plane contains points L, M, and N? Go ahead and shade it in your notes, whatever plane that is. And then what is the name of a line that is coplanar with JK and KL? So pause the video and finish that one up, and I'll show you the answers when you come back. All right, let's take a look. What is the plane that contains those 3 points? Go ahead and shade it. You should have a slanted plane, something like that. And then what's the name of a line that is coplanar with JK and KL? Here is JK. KL is right here. So the name of a plane might be, or excuse me, the name of a line that's in that same plane might be line JM. All right? So there are many others. It could be JM, it could be JL, okay, it could be ML. Those are all in the same plane. Here is your lesson check. Go ahead and do these 2 problems and bring your answers to class. We'll see you next time.